All right, so we're given the root of a binary tree. They want us to invert the tree and return its root. So we can see the binary tree is going to be comprised of a bunch of nodes. Each node is going to have a value. It's going to have a left pointer and a right pointer, which point to child nodes. And it's going to be like that recursively. So if you put a bunch of those together, you get a binary tree. And when they say inverse the binary tree, they just want us to switch what the left and the right pointers are pointing to. So that effectively switches the child nodes. So we would be flipping or like making a left-right mirror image of the binary tree straight through the root node, right? So which is like the very top node. So we can see like obviously the left and the right children are going to be swapped. It's just that the 7 is going to be where the 2 was, 2 is going to be where the 7 was, and then just taking us just a little bit of a look deeper here. Like if we look at this 2, the left child is also going to become, what the right child was. So it's going to become this 3, and then the right child is going to become what the left child was, so the 1. So it's kind of, right, it's like recursive. So it lends itself to a recursive solution. That's one way to solve this problem. And you can also do it iteratively. So if you do it iteratively, you can do it with a stack, which is like a depth first search, which kind of mimics the recursive solution. You can also use a queue, which is more of a breadth first search. The way I like solving this problem is with a stack iteratively, because it kind of mimics the recursive solution while not exposing itself to the risk of exceeding the size of the recursive call stack. Because some people kind of assume incorrectly that the recursive solution to this problem takes no memory, just because they can't see the code for the data structure. But in terms of the memory on the OS, it does have a recursive call stack, and that does take memory on the OS, and that can get exceeded, which could cause the computer to crash. So, I'm going to solve this. Yeah, long story short, I'm going to solve this with a stack and do it iteratively. But I think there's arguments to do it in different ways. But anyways, so just thinking about how that's going to affect the time and space complexity. The time complexity for this problem is going to be big O of n. So it's just going to be linear, where n is the number of trees in the binary tree, or the number of nodes in the binary tree. And then the space complexity for our iterative depth first search with a stack solution is going to be big O of n once again, because you can, in the worst case, if you have an asymmetrical binary tree, you can have literally every single node from that tree in the stack, like at a given point. So it's going to be linear with respect to the total number of nodes in the binary tree for the space from the stack. So yeah, asymptotically bounded, because just a quick reminder, like big O notation is like a absolute worst case. Like how can this function grow in the complexity, right? So it'd be asymptotically bounded by like this to some linear amount, right? As opposed to like some n squared amount or some n cubed amount. So actually let me walk through the problem as well, just before we get into the code for it. So I'm gonna just make a kind of a smallish tree here, and then just show what would happen for our algorithm. So we're gonna have a stack. At first we'd seed our stack, so we'd just put the root node in. The next thing we'd do is we'd start looping through all the nodes in the tree, basically by starting a while loop and then saying while the stack is not empty. So for each node, we're going to basically keep putting its children into the stack. So that'll allow us to iterate through every node in the tree. And then the way it kind of looks at each node, if you do test this yourself, like it'll basically just go down the entire left side as much as it can go before like retracing. So it'll do a kind of depth first search. But anyways, yeah, so we'll start by taking that top node from the tree. So we'll have this one, or this tree node that has this value of 1, and we'll basically, the first thing we're going to do is check if it's there, because I am going to push null children into the stack. So we're going to check if it's there. It is there. So if it is there, we're going to push its children to the stack. So let me just do that. Both of its children go. And then we'll just switch the children. So this left pointer will start pointing to the 5, and then this right pointer will start pointing to the 3. And after that, we're pretty much done with this loop. So then we go back to the top of our loop. We get the 5, pop it from the stack, put its children. Its children are both null pointers. So I'll just put those there to illustrate what would happen in that case. And then we would swap those children. So basically nothing would happen here. I mean, you have a left tree node pointer pointing to null and a right one pointing to null, and they'll technically, there will be some code that does this like no op thing where they switch, but that's fine. So it's still correct. And so those will be switched. And then next we go on to the top of the stack. So we take this node, we check, okay, is it there? No, it's not. So we do nothing. Okay, back to the top of the stack. We check, is the node there? After we pop it, no, so we do nothing. We don't push nodes, we don't swap. Okay, so then we're at the 3. We're gonna take the 3, pop it off the stack. Is it there? Yes, it is. So we're gonna basically push its children. So we push the 7 and then a null pointer. Okay, and then we're gonna swap its children. So the 7, which would have been over here, will now go over here. And then we have a perfect like mirror of the binary tree at the very end. Okay, but we still have its children or we still have the 3. We didn't look at no, we did look at the 3, but now we're looking at the 7, right? We would be, but not yet, because there's also a child that's a null pointer. So we would pop that from the stack, check if it's there. It's not. Okay, so we do nothing. Back to the top of the stack. We pop the 7. We check if it's there. It is. Okay, so then we switch its null pointer children, and we push them to the stack, which is like a no op. Okay, so then top of the stack, that one no op, this one no op. Okay, so you get the picture. So this is the algorithm in a nutshell. Let's go ahead and code it now. So the first thing we're going to need is a stack. We're going to need the ability to store tree nodes in a stack. So in C++, it's just stack, and then in angle brackets, you put the type. So it's going to be a stack of tree nodes, and we'll just call it st. Well, I don't want this to get too confusing what the variables are, so I'll call it node stack. But I also don't want them to be too long. It can be kind of tricky on these condensed time settings. Nevertheless, yeah, so we also need a node that we can use inside of the loop to basically be the node that we're looking at any point in time in the loop. So I'll just make a tree node pointer called node. We'll point that to root, and I'm not gonna use this root because we actually that's the solution. They want us to return that, so I'm just gonna preserve this value, and then so we don't forget, I'll return root already at the end. Okay, we also need to seed our tree stack, like I said, before we can do anything else. So I'll say node stack dot push, and let's just put that root node on to the top of the stack. Okay, so at this point we can start iterating through our stack while there are still nodes there. So I'll say while not node stack dot empty. So that basically node stack dot empty just checks if there's any nodes in the stack, and then if we do while not empty, then we know, okay, there's still nodes in there. So we'll do another iteration. So first thing we're going to do, let's take the first node from the top of the stack. So we'll say node equals node stack dot top. Okay, and then we're going to pop from the top of the node stack because we're done with it in the stack. We don't need it anymore in there. And then we're going to check, okay, does the node exist, right? Because we have to do this check since we're pushing children, which are null, regardless of the whether it's null or not. We're always pushing it into the stack. So that's why we have to do this check. Because if it's null and then we try to do the same for its children, well, it doesn't have any children, right? Because it's a null pointer. So we're going to get like a memory error. So what we have to do is check if it exists. If it doesn't exist, I'll just say continue, move on, go to the next iteration. Otherwise, if we reach this line of code, we know that it must exist. So let's push both of its children to the stack. So we'll say node stack dot push, and then we can push the left child, and we can also push the right child. Okay. And next up, we want to swap the children. So this is the part of the problem that's inverting the binary tree. So we're going to say, I'm going to basically make a helper method. So we'll say swap children, and then we're going to push the node into there. And this is kind of I would say like a 3-step process rather than a 2-step process, because you have to do something kind of, I wouldn't say fancy, but just slightly intentional here so we don't mess up the copy. So I'm going to make a private method. It'll just not return anything. It'll be return void. We'll call it swap children. We already gave it a name there when we invoked it on node. So it's going to take a tree node or a pointer to a tree node, and it's just going to swap its children. So, and the way we're going to do that is we wouldn't just be able to say node left equals node right, and then say node right equals node left. Like, this is the naive way to swap, and it doesn't work at all, because if we point this left pointer to just this right node immediately, then what happens to how are we going to keep track of the left node? So if you do this, like, you're literally just going to have 2 nodes pointing to the same thing. So this doesn't work. We have to basically save what this left pointer is pointing to first. So let's create a tree node pointer called temp, and we'll just use that to save the place of the that left node. So then instead down here, we can point this right node to temp. And then that's basically how to swap nodes. Swap nodes that are being kept track of with pointers. So let's go ahead and submit this. That's pretty much all there is to this problem. So yeah, hopefully this helps, and I'll see you guys in the next piece.